Hello everyone, I'm Robbie Sutherland and I'm here to present our work MIMO DPRNN ConvTasNet for the third Clarity Enhancement Challenge. I'm a PhD student supported by the CGT for Speech and Language Technologies based at the University of Sheffield, and this work is also supported by WS Audiology. So this talk today is going to be broken down into four main sections. So I'll give a bit of background for the system that I've submitted. Then I'll move on to an overview of the system and the individual components in it. I'll then move on to discuss the experiment setup used for training the system. And finally, there'll be a results and discussion section. So now to look at the background. So I originally considered the MC ConvTasNet system, which placed first in the objective evaluations for the first Clarity Enhancement Challenge. This is a source separation system trained to extract one speech source. The separation block in the system was based on temporal convolutional networks, which are used for source separation. These TCNs have since been surpassed by dual path RNNs. These have shown greater performance with fewer parameters for the source separation task. However, DPRNNs are yet to be applied in this low latency setting. So now I'll give a system overview. So I'll quickly break down the kind of acronyms in the title. So MIMO is multiple input, multiple output. So we get 6 channels of audio in. That's the 3 channels from the left ear and 3 channels from the right ear. And we get 2 channels of audio out. So that's binaural audio, 1 channel for the left ear, 1 channel for the right ear. The separation block in this system is made up of dual path RNNs, which stands for dual path recurrent neural networks. And then ConvTasNet is a kind of family of source separation networks, which use 1D convolutions to encode and decode the waveform. These are kind of analogous to the Fourier transform and inverse Fourier transform. So instead of getting kind of specific frequency representations, we get learned feature representations through training. So here's a block diagram of the system architecture. So there are 5 key components to this system. We have a spectral encoder, a spatial encoder, DPRNN blocks, a spectral decoder, and finally a null amplification block. The spectral encoder is, like I said, it's analogous to the Fourier transform. So we get feature representations from a left channel and feature representations from a right channel using 1D convolutions. The spatial encoder is also a 1D convolution, except this operates over all 6 channels of the audio input at once. This uses the same frame size as the spectral encoder, so we then concatenate these features in the feature dimension, and that's our input for the DPRNN blocks. These DPRNN blocks aim to estimate masks of our feature representations of our left and right channels, and we then use element-wise multiplication to multiply the left mask with the left channel and the right mask with the right channel. Finally, each of these channels goes into a spectral decoder, which essentially reconstructs the waveform from these feature representations as an inverse Fourier transform would reconstruct the waveform from frequency representations. The final stage is an LR block, which is an amplification for the listeners based on their audiograms for each ear. So the encoders. So we see we've got the 6-channel audio input. The odd channels are the left channels and the even channels are the right channels. The spectral encoder considers frames of each of the left and right channels separately. So this returns frequency representation, feature representations analogous to the Fourier transform. The spatial encoder operates over all 6 channels at once, so it's a 1D convolution with 6 channels of input. This uses the same frame size and stride as the spectral encoder, so that our representations have the same number of time frames. Now I'll look at the dual path RNN. So this is essentially made up of 2 RNN blocks, which operate over chunks of the audio. So a chunk is just a collection of frames of the feature representations. The first RNN is an intra-chunk RNN. This is a bidirectional LSTM, which operates over the feature dimension of our representation. So as you can see on the right, kind of displayed on the spectrogram, so the intra-chunk RNN operates kind of up and down the feature dimension of our system. The interchunk RNN instead operates over the time domain. Over the time dimension. So as you can see again on the spectrogram on the right, that's a unidirectional LSTM, which operates kind of across the spectrogram from left to right. By using the unidirectional LSTM, we're complying with any latency constraints because we're not looking ahead in the signal. So the first LSTM is a bidirectional LSTM, which then goes into a linear layer followed by layer normalization. This is then added to our input. We then reshape our representation so that the unidirectional LSTM will operate over the time domain. This then, over the time dimension, this is then input to a linear layer, followed by layer normalization, and then it's reshaped to its original shape. This is then added to the output of our intrachunk RNN, and then that's our output for an RNN block. This block is then repeated a number of times in our system. So the final stages are the decoder and the Nalar fitting. The decoder is a transposed 1D convolution which will reconstruct the waveform from our spectral encodings of each channel. This reconstructs overlapping frames of the waveform, so we use the overlap add method to handle this overlap. We also have the Nalar fitting, which is amplification based on the listener's audiogram for each ear. So now let's look at the experiment setup. So this system was submitted to task 2 of the Clarity Enhancement Challenge. So this is recordings with human participants wearing dummy hearing aid shells. In this data set, we have 6,000 training samples, 1,500 validation samples, 2,000 and 2,500 evaluation samples. When loading the data, we used 2-second sections of our signals, which included speech and non-speech segments. So as you can see from the diagram at the bottom, we kind of include sections of the signal where speech is not present, but also sections of the speech where the target speech is present. Now I'll look at the experiment setup. So the MIMO DPRNN conv-TASNet model takes audio and input sampling rate of 16 kilohertz. This is downsampled from the 48 kilohertz recorded audio. The frame size of our encoders is 32 samples, which is 2 milliseconds, and the stride of our encoders is 16 samples, which is 1 millisecond. The chunk size of our system is 5 frames. So each chunk that the DPRNN processes is 5 frames long. For our training configuration, we trained for 100 epochs with an initial learning rate of 10 to the minus 4. This was combined with an annealing factor of 0.9. So when the loss didn't decrease on the validation set after 2 epochs, we would multiply our learning rate by 0.9. And we use a combined waveform spectrogram loss, as shown in the formula in the bottom right, which was used in an entry to the second Clarity Enhancement Challenge. For training, we kind of decouple the denoising process from the amplification process. So our loss function takes as input the output of the spectral decoder for each channel. But then when we use our model inference, the output of the spectral decoder then goes through the Nalar amplification, which is fixed amplification for each listener. So our loss function is applied before our amplification. We also average the loss over each channel. So that's how we handle the 2-channel input to the loss function. A quick note on convergence. So you can see that the loss on the y-axis decreases as the number of epochs on the x-axis goes up, and we see that it starts to converge. A quick note on the latency and computation of this system. So the stride of the frames for the encoders is 1 millisecond, and the chunk size is 5 frames. This gives us a latency of 5 milliseconds from the chunking process. We don't use normalization in the time dimension, and our unidirectional LSTM on the time dimension means we have no look ahead from our LSTM. This provides a total delay of 5 milliseconds. Our model size is 1.2 million parameters, and this requires 119 million max per second. as a reference point, the spheric speech clarity DNN, which is in Phonac's recently released DNN hearing aids, requires 4.5 million parameters. So now finally, we'll look at some results and discussion. So this bar plot shows the scores of the baseline compared to our submission. So the HASPE score of the baseline is 0.19, and we increased this to 0.26. And the provisional listening test results that have been provided by the Clarity organisers increase this, show a score of 0.3 for the baseline, and we increase this to 0.36 with our submission. So we also look at the HASPE score versus SNR ranges, and you can see that across each SNR range, we see an improvement from our system. And this is especially apparent in the kind of middle range of -6 dB to 3 dB. And you can actually see that we kind of get equivalent performance at kind of equivalent, if not better performance at 3 dB in 3 dB higher ranges. So you could argue that there's a kind of an improvement of 3 dB on this from our system. So one of the concerns with this system is that there was no information about the target speaker. So there was no speaker enrollment module. And we were wondering whether this was causing the system to not perform as well as it possibly should have. So to look at this, we investigated the HASPE scores compared to the number of interfering speakers. So on the x-axis, we have the number of interfering speakers, and the y-axis, we have the HASPE scores. Of course, when there's no interfering speakers, there are, of course, other sources. So there's always 2 or 3 interfering sources present. This is just looking at how many of them were speech sources, because this is quite a challenging environment for speech enhancement systems. So you can see from this plot, from this violin plot, that we actually get very consistent performance based on the number of speakers. So while it's possible that a speaker enrollment system would have helped our system, it's also clear that there was more holding our system back. However, for each number of speakers, you can still get highly intelligible signals. So I'll play these for you now, play some examples.
I heard you the first time, boy. I had a hard job keeping my face straight. I didn't get back till nearly 1 o'clock. Oh, he had taste in his own way.
So as you can see, regardless of the number of interfering speakers, it's still possible for our system to get a highly intelligible output. Thank you all for listening, and hopefully we'll cut to a live version of me answering some questions.